Jasne, jeżeli wyraziłeś doktorat. Naprawdę? Do pracy. Dobra. I okej, ale jakieś emerytury?
Naprawdę się ale to jest kosmonauty, która została. Prawda, nie? Tylko to nie.
Okej, dobrze. I teraz co
ale właśnie ale nie, no to są nie lekacje, to jest tak
ale wystarczy tam się konfisky?
Nie, wiesz, to co by osób, co myślało,
Na zewnątrz. Rozumiem, mamy? So good afternoon, everyone. Today we are hosting, I wanted to say but no. Szymon Nakoneczny from Center of Astronomical Physics of Polish Academy of Science. Szymon was doing his PhD at the NCBJ here in Warsaw, and then he moved to Caltech, where he was doing his postdoc. And now he's back in Warsaw and gonna talk us about the catalog of quasars from the ZTF facility. So, the word is yours.
Thank you. So I will talk about the project I worked on during my 2 years postdoc at Caltech. The project was about classification of light curves from the Zwicky Transient Facility. The main goal of building a catalog of quasars. So let's start by introducing the basic ZTF survey. So this map shows number of observations equals in tiles of the ZTF survey. The survey operates since 2018. It has the median cadence, the time between the consecutive observations for part of the sky, 3 days, with some part of the data with better cadence at 2 days. The limiting demand magnitude of the survey is 2025. It observes the sky in G, R, and I bands, but in each of those bands, it provides separate catalogs. So it's not like for every object we have different magnitudes available. So for this project, we focus on the demand, which we provide as the most observations from those 3 bands. So the motivation for the work, my supervisor from the postdoc, Professor Matthew Graham, was interested in searching for the counterparts, electromagnetic counterparts for the gravitational wave events in the accretion disks of the quasars. So he did this work in 2023, where he found 9 possible candidates for such counter events, and he used the Million Quasar catalog to do this. So he took the quasars from the Million Quasar catalog and looked through the light curves of the Zwicky Transient Facility and tried to find the flares which match the events from the light of Virgo. This problem of searching for those counterparts can be difficult because the electromagnetic signal from the accretion disks can be either obscured by the accretion disk, or the quasar itself can be too bright to actually see this. So we may not be able to observe every such event, even if it occurs in an accretion disk. So my goal was to take ZTF data and create a catalog of quasars native to the ZTF survey, and also using the information from the light curves, so that it could be as complete as possible for this particular quest. So this is the project that I will talk about today. And it will be mostly about the methodology will be mostly about machine learning, and then I will also show how this final catalog looks like. So first, let's start with the training data. So since we will be working with machine learning models, we need to first have training data. So I used the SDSS spectroscopic confirmations to find galaxies, quasars, and stars. And this is the problem that I will be solving. So from the SDSS, I will take the confirmation, so the class of the objects, and then I will take the light curve of these objects and classify these objects based on their light curves. So this shows the distribution in given magnitude for the inference data. So this is basically the ZTF data which we want to run our algorithm to find the quasars of. The orange is the training data from the SDSS surface. So these two plots lines are normalized to unity. So it doesn't show the difference in the number of objects, but the difference in the distribution between these two sets. And these lines show the distributions of galaxies, quasars, and stars in the training data. These are also normalized to unity, but then divided by 3 just to show the differences. The reason why it's important is for two things. One thing is that we want to make sure that our training data covers the magnitude range of the inference data. And the other thing is we want to see how these two distributions differ. And the reason for that is when we run inference with machine learning models, we get some scores from these models, and this is called probability. But in the reality, once we run the inference, it's not actually probability, because probability in this sense would be if we, let's say, have take 100 objects which has 80% of them are classified to be quasars with 80% probability of being a quasar, and actually 80 out of those 100 objects should be quasars. But that would be true only for this distribution. But when the distribution of objects in the training between the training and inference data changes, in this case, it's not a color space because we are not running inference in color space, but we are using light curves. But since these are different, the densities of objects, the difference between the number of the classes between training and inference data will be also different. So this probability will no longer be probability. So these are two things important to keep in mind. So this is the training data that we will be using. And now I will talk about the machine learning model. So the model which I was using is based on the attention mechanism. So this is this famous mechanism right now, which is behind all those large language models. And so previously, if we had any kind of time sequence and we wanted to process it with machine learning, we had to provide, apart from in the case of light curves, the magnitude value, also time of observation, so that the model actually understands that this is a sequence. The attention neural networks work in such a way that they see the whole light curve when they are processing every part of the light curve. They can see the full light curve. So the recurrent neural networks, they went from left to right. Let's say they went one by one, and they had some states, and they changed that. The attention mechanism looks at the whole thing in every moment of its processing. So we also have to provide this information about the time somehow to the neural network. So the positional encoding is a way to add this information to the neural network so that at each time when it's processing a part of the neural network, it can actually understand the context of the time of this observation within the full light curve. So let's skip this. This is example from natural language processing, but this is the example from the network that I'm using. So the network itself is called Astronomical. It was implemented in Chile by this author, and he's actually a computer scientist who also works on the astronomical problems. And this is the positional embedding. So these are the time steps. So let's say we have a light curve. We have 200 time steps in this light curve. So they have the time of observation, and every time of observation is then translated to one row of this matrix. And this row is given by sinus and cosinus functions with different frequencies. In every column is a different frequency. So basically, then at every point of the light curve, the machine learning model sees the position of this part of the light curve as different values for different frequencies, basically. So in this way, at every point, it has a full information of the time position in the light curve. So basically, the input of the machine learning model is a vector of the magnitudes, and then this full matrix which encodes the position, the time of observation. So now this is probably rather well known. It's a structure of a standard fully connected neural network. The reason why I'm showing this is to show the difference between the size of just a fully connected layer and the model which uses the attention mechanism. So here, if these are some inputs, some magnitudes of the light curves, these are the weights of a neural network. So basically, a matrix like this represents weights of the neural network which are tuned during the training process with the backpropagation algorithm. And then we have some output of such a layer. So one layer like this represented basically with a matrix of weights. And this is a network with attention mechanisms. So I will try to explain shortly how attention mechanisms works. But since it is maybe a bit complicated, let's see if I will manage to do this well. So in attention, we have three matrices. This is one attention, let's say, layer, or it's mostly usually called attentional head. It has three matrices like this. So basically, one attention head is constructed of kind of three fully connected layers. And what happens is this example from natural language processing. In natural language processing, every word is represented with some vector of numbers. And let's not dive into this at all, how these are created. In our case, this is basically there is one more thing in the implementation of this attention mechanism for light curves. So every value of the magnitude from a light curve is first passed through a fully connected layer to create embedding of this one value in that case in 256 numbers. So basically, in our case, or maybe I will explain that in a moment. So let's focus on the natural language processing. So we have a matrix of inputs. So we have different time steps of this different next words in a sentence. In our case, this would be the next values of the light curve. And this input is multiplied by these three matrices. These are called query, key, and value. This comes from relational databases. And basically, the idea here is that the query represents a word which the machine learning model is processing at the given moment. The key represents the values of all the other words in a given sentence. And the idea here is to match these two representations so that we can look at which words in a sentence are important to understand the given sentence at which we are in the given word at which we are in the sentence. So the example would be that we have a word bank in the sentence, and bank can mean different things. So it can be, for instance, a financial bank, or it can be a river bank. And so as an input here, the bank always has the same representation, but the context of this word actually changes what it means in the sentence. So the attention in this sense would look at while processing a word bank, the idea here is that we have higher score at words either river or financial, because that's something that affects the bank. In case of the light curves, we could have some value of the magnitude, let's say 20, and in that sense, the model may want to understand whether it's a peak of this light curve, whether it's a valley in this light curve. So let's say that this a peak in this light curve, so it could give higher attention to other peaks in this light curves to, for instance, understand the time between the subsequent rises of flags. So the way it works is that at every word in the sentence, first this representation is multiplied by the query key and value matrices, and that provides this matrices. And then what happens is that basically every row from this matrix is multiplied with this matrix, so it's transposed also with every row over here. And in the elements where the representation of these two rows from these matrices are similar, the dot product will be higher. So in this sense, the network learns to match these words which are important to understand each other by giving them similar representation in keys and queries. And this is represented over here. When we multiply the queries and the keys with each other, we'll get a quadratic matrix. And this matrix will be the attention matrix. So if we look at this matrix at a row which corresponds to the word bank, we would then find at the position of the word river or the financial higher value of the attention. Then this is the softmax is basically a function which changes values into probabilities, so that the score is probability, and then this is a quadratic matrix, and then we again multiply it with B in order to get a matrix which is the same size would be the Z0 over here, which is the same size as input. And what happens is natural language processing is that these matrices are then added together element-wise. So basically, again, given the word bank, what happens is that first we have the same representation for word bank in every sentence, but after the processing of the attention, what happens is that we add the context of this word in the sentence to this original representation. So the representation for these words will now also have the information about the context of this word within the sentence. And then what happens next is that we are not using only one attention head, but we are using multiple attention heads, and that's what's represented over here. Then we concatenate all of those. We do some other pre-connected layer in order to kind of average these representations into short representations. and we end up again with something that is the same size as the input. But the difference is that for every word from here, we add to this representation the information of this word in the given sentence. So what does it actually mean in the sentence? What's the context of this word in the sentence? And for the light curves, like I said before, that would be that would mean that how let's say we have the magnitude value 20, and what does it mean with the context of the whole light curve? Is it a peak of the next of something that is repeating in this light curve, or is it a single peak, or is it a noise fluctuation, for instance? This kind of things. So that's how attention works. This is a visualization again from natural language processing, where we take word making and we take the attention matrix for this word, and since there are many different attention effects, the colors mark the maximum value of attention for this word in this sentence. So while processing word making, it looks mostly at more difficult because it's making more difficult what matters most in this case. Okay, so that's how the attention works, and now going back to astronomy. So how we can implement that for astronomical problems. So in this implementation, it's called Astronomer. This is the structure of the network. So we have the observation times of the light curve, and we have magnitudes. And this is basically, and this model is limited at maximum 200 observations in the light curve. It's just how it's implemented. And so these are 200 times of the observations and 200 various magnitudes. And then the positional embedding takes this vector and changes that into a matrix which encodes these times at different frequencies. And then there is also a feed-forward network. The feed-forward is, but it's basically a fully connected layer. It's actually two fully connected layers. But the size of this is 1 times 256. So the input here is one value of a magnitude, and the output is 256 values. So basically, the network takes one value. Every value of the magnitude is translated to 256 values, new values. And the reason for that is that when we look at the positional embedding over here, basically what happens is that I can say that the positional embedding is actually added like element-wise to the representation of the of either the words or the light curve. So basically, we have two matrices and we add them together, and that's what's then fed to the network. So basically, if we let's say take a light curve over here, which has some values of magnitudes, say 19, 8, and 20, and we add it just like this, what happens is that these values of magnitude will destroy the positional encoding. So this embedding, which the network learns to embed every magnitude value into 256 new values, which matches the matrix size of the positional embedding, is made so that the network can learn how to do this without actually destroying the information of the positional embedding. And after that, these two are added together like element-wise, and we end up with a matrix of 200 times 256, where 200 is the number of observation steps in the light curve, and 256 is basically a parameter of the neural network. We can have it however we want. But the important thing is that the positional embedding and the frequencies that are used there actually cover the range of the frequencies that we are interested in the light curves. Okay, and then there are the self-attention blocks. The self-attention, it's called self-attention because we use the attention mechanism on the original. We have just one input and we use the attention on this one input. This is self-attention. There is also cross-attention, which which was used for the translation, where we have one sentence in Polish language, another in English, and the keys and queries are taken from these different languages. But this doesn't matter. Mostly right now, most of those big models are using the self-attention mechanism. So there are two self-attention layers which create the representation, and this representation is again 200 times 156. So in this level, basically for every time step of a light curve, we have a representation which tells not us, but the network, something about this particular value of a magnitude within the whole light curve. And this is the representation that the attention models create. And how this network is trained? The original training of this network is done in the so-called semi-supervised way. So from the original data, let's say that this is a light curve. So sorry, different magnitude values over here. And half of these magnitudes randomly, we choose half of those magnitude values, time steps, which we mask. So the model does not see it as an input. It sees that there are objects which are masked out at these time steps. And then it is tasked with recreating those missing values from a light curve. So if something is masked, it's also not seen in the attention, so it's like completely not visible to the machine learning model. Then there is also a mechanism where some of the values are changed for false values actually, but these are all more like technicalities. It's done so that the model is not biased by this masking. I would call it more technicalities of training machine learning models in this space sense. So it doesn't matter that much. So the way that the model recreates this light curve is by taking representation and then having under the feed forward, so the fully connected layers, which are of size 256 times 1. So it basically takes each row of 256 values from this representation, and based on those 256 values, it recreates the magnitude value. So this 256 values actually has to have full information about the context of time of this particular value that is recreated in the full light curve. And then this is the original training, which takes the longest time. But then what can be done is we can remove these parts actually. And take only these parts which create representation. And after that, we can also add some other fully connected layers, which will learn to classify objects based on these representations. And this is called the fine-tuning part, when we actually take this previous part of the network and then fine-tune it to another task. Okay. So that's these are the last slide about the astronomer, but these are the original results of the paper which presents the astronomer work. So these are again not narrative results, but I want to show this to highlight how this training procedure originally looks like. So what we have here is the authors here took training data from Warsaw, and they took light curves from the galactic bulge. And they have 1.5 million unlabeled light curves there. And first, they trained the model to learn representations for this 1.5 million of light curves without knowing what kind of objects these are. The model just learns to recreate the light curves of any possible type. And this original training takes they use NVIDIA 800 GPUs, and it took almost 10 days. And then they took smaller data sets from much of 21,000 labeled variable stars. I don't have a list here of all the different classes of the variable stars. They have several of these. They also take a set of labeled variable stars from OBE. This is more than 300,000 objects, and from Atlas more than 400,000 objects. What's important here is that from all these data sets, they use different filters. They have a bit different cadences, 4.7, 3.8, and 2.9 days. So there are differences between these data sets, but the original model is trained on this large data set from Macro, and then it's fine-tuned to classify variable stars in these three different terms. So this then shows the time that is required to fine-tune this model. And this is 23 minutes, 9 hours, and 1 day. So it's much shorter to then fine-tune these models once they are trained originally. And this is this concept of the foundational models, when very large models can be trained on full data from a given story without consideration of what is the final goal that we want to use, and then it can be fine-tuned in much shorter time to these particular problems. Well, okay. And now let's move back to the Zwicky Transient Facility. So what I did is the authors of Astronomer, they also did this original training of the Astronomer model on the ZTF data. And then I took this model which was pre-trained on ZTF data, and I wanted to use it to build a catalog of quasars. So what I found in order to achieve the best results of particular quasar classification in ZTF data was that first I had to retrain this, finding this model in a couple of stages. First, I trained it in, again, the same supervised way, but originally it was trained on the fifth data release. So that was about maybe 2 years or something like this. Sorry, I don't remember right now. But when I was using when I was in this catalog, the current data release was TLDR20. That was 6 years of observations. So that first we trained in the same supervised way to the 20 data release. And then I fine-tuned the model to the classification problem on the training data. For every light curve which is longer than 200 observations, I randomly chose the 200 observations from every light curve, which basically gives the highest, the longest time span available in for those light curves. The authors of the Astronomer originally, they didn't sample the observations randomly, but they took windows of 200 of consecutive observations. But for quasars choosing these observations randomly, I think because it gives longer time span, it works better. And then there was also a project in the ZTF at Caltech, also for classification of objects, but using pre-computed features. So they had a set of 50 or 60 features which describe the variability of light curves. And it takes for the full ZTF data, took something like 2 months or something to calculate those features. And basically using non-deep learning models, I managed to achieve 81% of the quasar F1 score. So F1 score is basically a harmonic mean of the purity and completeness for quasars. Where with the transformer model, I managed to achieve the 89% result. So there is quite a big difference in the quality of the classification, but also the retraining of the Astronomer took 1 day in my case, with the original training also, let's say even 10 days or something. So the whole deep learning approach is actually much shorter than calculation of the of some standard features. And the 95% comes from because this is based on the, I think, per data release, shorter light curves, where the compute the standard features were available, and they were not available for the latest data release because they took so long to compute. On the DR20, the quality of the classification from the learning was 95%. So now these are light curves from these are quasar light curves from ZTF. They are here sorted with the redshift, so it's 0.5, 0.9, 1.5, and 0.3. So here, first thing which we can see here is how the light curves from the ZTF survey looks like. So there are sometimes when there are no observations due to either full moon or technical breaks. And we can also see the variability of quasars. We see that they are variable on all the timescales that we have available here in the observations. And in some cases, the variability of quasars is at the edge of the signal to noise of the ZTF. So this is the task for the machine learning models to learn to classify this variability against the variability of galaxies and stars. And these are all the light curves of quasars, which our model also classifies as quasars. So you can see that the classification for this is like 99%. And then here are light curves of objects which SDSS classified as galaxies based on the spectrum, but our model classified them as quasars. And you can see that the probability is either 99% or 5 or 64, some different levels of confidence. We randomly chose 3 of them, and Professor Daniel Stern took these objects and wanted to see whether they are actually galaxies or quasars, and found that from the SDSS spectra, this was already actually quasar based on the SDSS spectra, and the classification in the SDSS was incorrect. And then he took these two and ran spectroscopy at Palomar for them, and he also found that these are also quasars. So this is important because when we have some metrics like, let's say, 95% or 90-something%, having misclassified objects in the training data means that actually achieving 100% accuracy or precision of whatever is actually incorrect, right? Because some objects, that would be actually an overfitted model, because some objects can be misclassified in the training data. Okay, and this shows on the y-axis again quasar F1 score. And we want to see how this score depends on the value of the G-band median magnitude, also on the value of the error, and the number of observation epochs in per each light curve. So we can see that the 5 sigma limiting magnitude is about 20.5. So over here we can see that the blue line is the ZTF classification. It drops rather quickly from for fainter data. Then the orange comes from the classification from Pan-STAR scholars. So I will also take colors from Pan-STARs, WISE, and the proper motions and parallaxes from Gaia to also compare this classification from ZTF to this other service. So here we have Pan-STARs because the Pan-STARs has coverage for almost all of the objects from the ZTF. So this the gray line shows the distribution of the objects. When we add Pan-STAR colors, then the green comes from adding these two things together. So the adding is done with the extreme gradient boosting model. So basically there we take classification from the light curves as features, and also features from this other service. Then the faint end is we get better results at the faint end. But this mostly comes from the fact that Quasars has better signal to noise at this faint end of the data. If you look at the mean magnitude error, is the same thing. The magnitude and error are highly correlated, and we see the same thing that with the higher error, the results of the classification drop significantly. Although most of this classification in the catalog will stem from too high noise in the observation, which happens mostly on the faint magnitudes. And then the last thing is the number of observation inputs. So here we can see the 200. Here are the 200 observations, which is the limit of the input of the machine learning model. So you can see that the scores rise rather sharply up to the 200 observations. And then they stop because simply we cannot. So they are likely to have higher number of observations, but we undersample them to 100. And that's why we don't see any improvement over here. So it means that for Quasar classification, we definitely would want to prefer to use a model which can actually process more than 200 timestamps. Okay, this is again the Quasar F1 score in every cell. And this is the number of objects in every cell, and the cells are divided for magnitudes, value, and the number of observations. So we can see that the scores deteriorate with both the either lower number of observations in light curves or higher magnitude. However, the limiting magnitude is 20.5, and we can see that we can actually go even one magnitude beyond the 5 sigma signal to noise limit if we have high enough number of observations in the light curve. We remove this part of data from the final catalog because the quality of the inference here is not good enough. We also wanted to answer a question: what are actual requirements in terms of time span of the light curves and the cadence of these light curves for Quasar classification? So before in this plot, one problem with this analysis is that if we don't have a lot of objects in some cells, the model can also work worse in these parts of the data because there is not enough objects there. So I also created this experiment where I took every point here is basically a result of a new machine learning model and the new training data. But light curves in every point have similar characteristics. So they have the same time span and the same number of observations, which translates roughly to this, the same or very similar cadence. So with that, we can actually see that, let's say, if we look at the threshold of 90% classification score for Quasars, and we take the highest time span of cadence of 3 days, we can see that we roughly need about 800 days of observations to reach the 90% score. And then at the highest available time span of 6 years, we also kind of arrive at some kind of plateau here that the scores don't improve anymore. But we can also take a look at the highest time span, for instance, and rather lower worse cadence, longer cadence. And we can see that even at about 12 days cadence, we can also achieve about 90% Quasar F1 score. So this is important, for instance, for service such as LSST, where people wonder for how long should we run observations until we can get good quality of classifications from the light curves. And this I will skip. And then For the final catalog, I also wanted to answer the question whether it's enough to just take classifications from the light curves or whether we also should add features from other service. So here I consider the Quasars, which has the UGRI, very correctly, magnitudes, WISE, W1 to 4, and parallaxes and proper motions from Gaia. And this is the feature importance from the extreme gradient boosting. So this has all of the features from all these different services, and the PLC QSO, this is the probability from light curve of the quasar classification. And this is an experiment where I required that all of these features are present in the training data. So we can see here that the W1 minus W2 are the most important features for quasar classification. And this is not quasar versus galaxy versus star. This is quasar versus rest. So the galaxy and star are like merged together, let's say, so that we can actually see the importance of features only for quasar classification. But there is about 50% importance of the classification from light curves, which means that not all of the quasars can be actually classified with not all of the quasars which have WISE observations available can be classified based only on WISE data. But there's this, it's not exactly 50% of objects. This is a story, it's more complicated. It comes from how much basically this machine learning extreme gradient boosting model uses these features in the classification trees. And then when we look at comparison of the classification, for instance, with WISE, we get from only classification based only on light of 97% score, only from WISE 98% score. So it's similar, same with Gaia, 97 versus 26%. But again, adding this together gives good result. So based on that, we conclude that it's important to also use WISE features for the final catalog, and that's what we also did. And we also predicted photometric redshifts from the WISE data. WISE observations are available for about 1/3 of the full year data. So for about 1/3 of the catalog, we also have photometric redshifts. And this is so the last two slides. This is the number of objects we get in the catalog as a function of the quasar classification probability. So basically, when we take all of the objects which are classified as quasars, we get 46 million of objects. But a lot of them have low probability of classification, so there will be a high contamination with galaxies and stars. And the reason why we cannot take this is this difference that I mentioned at the beginning between the training and the inference data. If the training and inference data were very similar to each other, then we probably could take all of them. But since the spectroscopic data has some color selection functions that pick some subset of the data, we cannot take all of them. And the 5 million comes from taking the cuts on the magnitude and the number of observations and the probability of the being greater than 90%. If we look at the distribution of photometric redshift in the catalog, we can see that if we take a sample which is limited at 99% of quasar probability, we get this distribution which looks like here. Then the 90% is the one over here. And then if we go to this low probability quasars, we get influx of objects at higher redshifts. This would be something interesting to follow up to see if these are actually some higher redshift objects, but with lower probability of classification. And the data, we publish the data into files, the 5 million of the objects, which is a smaller file, easier to download, and also all of the 550 million objects classified as quasars. And if someone was interested in the work with catalog, I also have all of the predictions and all of the light curves on a disk with me, so it's easier to access also like this. And that's it. Thank you very much.
Thank you, Szymon. Any questions, comments? The speaker? No?
Yes, suppose you have a transient in HCM due to merging of variables in this amount of HCM. So this changes the likelihood of the quasar because you see some transients. Would your neural network classify such an object as an HCM, or would it treat it differently?
Yeah, it's a very interesting question because if in the training data, let's say that this flare somehow makes it more similar to some supernovae, for instance, or there is a reason why this would be more similar to galaxies or stars, and there is many more of flares similar like this in galaxies and stars, then the model can be actually biased towards predicting this as a quasar. So this is a very interesting thing to actually see in finding the cut-off. But even if you have a flare like this, you also still have the full variability of a quasar, right? So I think the model should learn that there is still this pattern of variability of quasar. But it can be that it would be, let's say, misled by this fact, because there's also the vectors are normalized to unit mean, but they are not like squashed to say unit standard deviation. So if you have a bit like this, it would make it would still the network will still see that there is a variability from quasars. The fact that you have this flags will not like lower the variability, the other variability as the input for quasars. So it shouldn't. It literally shouldn't. Yeah.
So in some cases you have to just pick 200 data points, even if it has a larger number of data people like that. How long would it take to training a network that was like as an input a large number of data points? Is it worthwhile?
So you have the input is you have the 200 times 256, right? So if this case quadratically, so if you have if you take 200 more observations, well, this will be twice as large, right? So but the network wouldn't be that much larger. So it's hard to predict how that would scale. I think I don't know how that would scale. But the number of time steps in every point of the network, you have the matrices which are in this case 200 by 256. So if you have it 400 times 256, the whole network would be twice as large, right? So you would need twice as much memory in your GPU. So this would be the biggest limit here is the memory in your GPU. So we are mostly limited. The size of the network is mostly limited by how much you can put on your GPU, right? So in that case, probably it wouldn't fit on this particular GPU that it was training. So that's the biggest issue. And then for the training time scaling here, I wouldn't be sure how that would scale, but also would be longer. But the memory would be the biggest issue.
More questions, comments? To ask about this double, the one slide before, this double distribution. See the lowest probability one. Why is it so like this? I mean, like,
you mean the lowest probability is this one over here, right?
It's triple.
Yeah. So this is very interesting because the prediction of redshifts comes only from WISE colors, but the classification comes from the light. The probability of the classification comes from the light waves, right? So there is definitely correlation here for the noise. So the which are fainter will have higher noise in light waves and also in WISE observation probability. So because of that, they will have lower scores. And somehow the machine learning models learn that probably objects which are fainter, which are fainter, have higher noise, and are probably higher redshift objects, right? So that is what we learned to predict higher redshifts. So it can be real, but can also be biased completely. So because they have slow classification score, it would probably require some additional technique to see whether machine learning models are actually correct here or not.
Just easy question, and for photos, you use not only WISE and Z information, ZTF information, but also the other survey.
No, only WISE.
Only WISE.
Only WISE, yeah. On other data also would help, but completely honestly, I just ran out of time, and it takes a lot of time to cross-match all of those different services, and I was finishing my postdoc, and I could also only
have to
finish with WISE, yeah.
Okay.
But WISE was the most important, so. But one can still improve the catalog by adding probably other stuff.
Not, let's thank the speaker.
Thank you.
Thank you, Shimon. And the notebook is somewhere there. Next week, there's long weekend. It's a bank holiday, so there's no seminar next Tuesday. And in 2 weeks, we will have a talk of Łukasz Proszykowski from our Observatory. Thank you very much.
Jeżeli jakby znaczyliście redshifty do jednej trzeciej tego, co robimy.
Idę
Tak.
Szanowna Pani,